Greetings, class. I'm going to be covering additional derivative topics in section 6 concerning related rates. In this section, our goal will be to solve related rate problems and applications. So when we are looking at related rate problems, there are typically 3 variables instead of our just x and y variables. Typically that third variable is the independent variable related, or often time. Our number one goal is to find a formula for the rate of change of one of the independent variable terms. And these problems are solved by using relationships between variables, differentiating or finding the derivative, and solving for the term you want. So let's take a look at our first example. A weather balloon is rising vertically at the rate of 5 meters per second. An observer is standing on the ground 300 meters from the point where the balloon was released. At what rate is the distance being observed and the balloon changing when the balloon is 400 meters high? First things first is you want to get a picture of what's happening, and that's exactly what we do in the next slide. So you can see we've drawn a picture. Part of the solution, the first part of the solution is to make a drawing. Notice the independent variable is time. Which quantities that change with time are mentioned in the problem? Well, we know that the height of the balloon changes with time, and the distance from the observer to the balloon also changes with time. And we can also look at this picture. Here is our balloon. We have our distance y here that is changing with time. We have our original fixed distance of 300 feet from the person to the initial point of release. And then we have this distance x that's changing with time. If you notice, we've been able to draw a nice little triangle. And so our math would tell us that we can use Pythagorean theorem. And so notice we have, 300 squared, which is basically, x squared plus y squared. And this should technically be the hypotenuse, right? But for purposes of this problem, we will keep it as x. And so again, the base and the 2 legs squared is equal to the hypotenuse squared. So if we take the derivative of this equation, you can see that here that this is the derivative. The derivative of 300 is 0, right? The derivative of y squared here is 2y. And then notice we're doing dy dt because we're differentiating with respect to t. And the derivative of x squared, just using the power rule, is 2x. And then again, because we're differentiating not with respect to x, but with respect to t, so it's 2x dx dt. So we are really wanting this dx dt, the rate at which the balloon moves away from the observer, if you remember from the original problem. And so when we take this original problem, we're going to solve for dx dt. And you can see here that if you divide both sides by 2x, you can be left with dx dt by itself. And then if you notice, you have divide dx dt is equal to 2y dy dt over 2x. And that cancels, leaving us with our final solution, y over x dy dt. Now we have all of this information. Dy dt is 5 meters per second. We know what y is for a given point in time. And we have, and then we can solve. So you can, few things that we have to find. We know what y is, and we know what dy dt. In order to solve this problem, we needed to find x. So again, we're going to use the Pythagorean theorem, right? The original problem was x squared is equal to 300 squared plus y squared. And so if you plug in 400 for y right here, you'll find that x is equal to 500 when y is equal to 400. And so once we plug this number into our differentiated equation, we can find dx dt, which is 4 meters per second. So solving related rate problems, that was an example. But the first thing you need to do is make a sketch. This is the most important thing. You need to visualize what is happening. Then you need to identify all of the variables. What information are they giving you? And figuring out what they're wanting you to find. Now express all your rates as derivatives. So the rates, for example, in that particular problem, we knew that the balloon was rising at 5 meters per second. So rising vertically, and we figured out dy dt is 5 meters per second. Now we find equations connecting the variables. And so in this particular problem, we had a triangle, right? So we were able to use a squared plus b squared is equal to c squared. And then we took the derivative of this equation. So whatever you find in step 4, you're going to take the derivative of the equation you found in step 4. And last but not least, you solve for whatever it is that they're asking you to find. Let's do one more problem. A rock is thrown into a still pond and causes a circular ripple. This is your first bit of information that you're using a circle. Okay, and which is nice. They give us the formula here, right? This is the formula for the area of a circle. It's telling you that the ripple or the circle grows at 2 feet per second. Okay, the radius of it. So in this case, this is dr dt is equal to 2 feet per second. And how fast is the area changing when r is equal to 10? So this is another bit of information. So again, picture, that's the first thing that they do. Make a picture. We identify the variables. We're going to let r equal the radius and a equal the area. So as I said before, you've already found dr dt and you've already been given the radius. So now we just need to find the derivative of d a dt. Now pi is a constant, and this is just a simple power rule. So you take that 2, bring it down, and this becomes r to the 2 minus 1, which is just r. Now again, you're taking it with respect to t, so it's dA dt. Pi stays the same because it's constant. You brought that 2 down, r, and then dr dt. Now you have all of your information. You have r and you have dr dt. And once you plug that in, you have 40 pi, which is 40 times about a little bit more than 3, so a little bit bigger than 120 feet per second is the rate at which the area is growing. All right, and one last problem is, suppose that for a company manufacturing transistor radios, the cost and the revenue equations are given. And so let's read the information where the production output in 1 week is X radios. So we know that X is the amount of radios made. If we increase production of radios at 500 per week, when production is 2,000 radios, find the rate of increase, the cost, and the revenue. So we're going to be really doing 2 problems, right? One involving the cost and one involving the revenue. So let's take a look at the cost first. we're basically going to take the derivative of this function, 5,000 plus 2x, with respect to time. And so this is nice because the derivative of 5,000 is 0, and the derivative of 2x is just 2. And so here is our derivative. dc dt is equal to 2 dx dt. Now dx dt from the beginning is the rate of increase is 500 radios per week. So the cost is going to increase by a rate of $1,000 per week. Now the revenue, we're going to take the derivative again. So the derivative of 10x is just 10 dx dt, right? The derivative of x is just dx dt. Now this is a constant, so that's going to stay there. We're going to bring that 2 out to the front, and this becomes x to the 2 minus 1, which is just x right here. And then the derivative of x is dx dt. So this is our derivative, and we have all of that information, right? X is 2,000. You know, that's where the increase will happen once we make 2,000 radios. dx dt is 500. And so you plug all of those values in. So we should get a revenue increase of $3,000 per week if we increase the rate, the number of radios by 500 radios per week. And that is it for this session. Now we will review for the midterm.